Today on How It's Made. Aluminum pots and pans, artificial limbs, peanut butter, and the high-intensity light bulb. There are several different ways to manufacture aluminum pots and pans. Some factories have giant machines that simply stamp out or mold the cookware, while other factories use a technique called metal spinning. To make cookware that's safe for food use, the aluminum must be pure, no other metals mixed in. It all starts with a round aluminum sheet called a blank. They stamp the pot size and company name on what will be the bottom of the pot. They clamp it onto a lathe, centered against what's called the chuck, a metal mold shaped like the inside of the pot they're going to spin. The lathe spins at 2,000 revolutions per minute. Guided by computer software, the spinning tool, a round wheel made of a special plastic, pushes against the chuck, stretching and shaping the aluminum blank, much the way potters stretch and shape clay against their hand on a pottery wheel. Except that metal spinning works sideways, not up and down like pottery. The machine trims off excess aluminum as it rounds the edges. The factory has no use for these very sharp metal leftovers, but it doesn't throw them out. Aluminum is difficult to mine and therefore very expensive, so scrap aluminum is sent off to be recycled into other products. After the final trim to the finished size, another trimmer moves in to take the sharpness off the edge. It's taken 4 minutes to spin this 32-liter pot. Now it comes off the lathe. They punch out handle holes. Then rivet on aluminum handles. The pot is now finished. Items that aren't as large and heavy are spun on a hand lathe. This is where you need an experienced metal spinner, because this trade isn't a mechanical science. You've got to have a feel for it. Besides cookware, many other aluminum products are spun on a lathe. This is a light reflector, that round aluminum fixture that covers light bulbs in factories, stores, and arenas. When working the hand lathe, the metal spinner uses what's called a scissor tool. It's the equivalent of the plastic wheel on the automated lathe. As the blank spins, he moves his tool further and further down to stretch the aluminum into the right shape. This is a sausage funnel. And this will be the inside tube of a cake pan. He makes the body of the cake pan on a different lathe, using a variety of tools to get a variety of effects. This beading tool creates an edge, for example. Almost all metals can be spun, though some are better suited for the technique than others. Aluminum and steel are very formable metals, so they provide the best results. Can a baking ingredient be the answer to global warming? Canadian researchers have found a way to transform harmful carbon dioxide into harmless sodium bicarbonate, baking soda. They mix CO2 with water, then force it through plastic balls treated with an enzyme from alfalfa. Today's artificial limbs are a far cry from the wooden leg of yesteryear. They look very realistic, and thanks to advances in prosthetic technology, artificial limbs function more and more like the real thing. They start by measuring the amputee's stump, what doctors call the residual limb. First, they measure the circumference at different points. Then the diameter at different points. They protect and lubricate the residual limb by coating it in petroleum jelly. Then they immerse it in algin, a gelatin-like substance that comes from algae. After about 5 minutes, they remove the residual limb. The algin has already begun to stiffen and maintain the limb's shape. A couple of hours later, it's stiff enough to be used as a negative mold. They pour in plaster of Paris, then insert a metal rod. The rod is what will later allow them to mount the dried plaster to work on it further. The plaster takes about an hour and a half to harden. They cut off the algin. Then, using sandpaper and files, they refine and smooth the surface. This plaster copy of the residual limb will now be used as a positive mold to cast the artificial limb. Often, they use a different technique to make the positive mold. They build a negative mold first using strips of plasterized cloth, much the same way they make a plaster cast when you break your leg. Then a scanner takes a detailed three-dimensional reading and programs it into a computer. A technician then makes any necessary modifications. They put a plaster block on a cutting machine. The computer guides the blade to carve out the positive mold. With either technique, once the positive mold is ready, they can make the artificial limb. The process they use is called lamination. First, they cover the mold in fabric socks. Some made of nylon, others of a material that contains fiberglass. They layer 6 to 10 socks in all, depending on how rigid they want the artificial limb to be. Then they coat the socks with a liquid resin made of either polyester or acrylic. Here they're using acrylic tinted to look like Caucasian skin. It's important to ensure the surface is evenly soaked. It's a meticulous process that takes about an hour. The acrylic solidifies in about an hour. Polyester takes about 12 hours. They then break the plaster mold inside, leaving a durable plastic shell called a socket. That will be the basis of the artificial limb. The socket connects to another plastic shell containing the mechanics. Or, like this artificial leg, the mechanism can be modular and covered in just a skin-colored foam. If the muscle at the site of the amputation still emits a good electrical signal when contracted, the patient can get a myoelectric prosthesis. It has an electrode that captures and amplifies a signal, triggering the artificial hand to open and close. As early as the 1400s, Africans made peanut stews. Peanut butter, as we know it today, was invented in 1890 by an American doctor. He used it as a protein substitute for people whose teeth were so bad they couldn't chew meat. The best peanuts for making peanut butter are runner peanuts because they're uniform in size. They roast more evenly than peanuts that vary in size. They arrive at the peanut butter factory already shelled. To make a 500-gram jar of peanut butter, it takes 565 grams of peanuts. That's about 1,100 peanuts. The first step is to roast them. The nuts travel through a hot air roaster heated to 204 degrees Celsius. The shaking motion moves them around so they roast evenly. More than 3,600 kilograms of peanuts go through this roaster per hour. When they come out, they've turned from white to light brown. Next, they go into another machine, which fast cools them at room temperature using suction fans that circulate air quickly. This rapid cooling process is critical. It halts the cooking and prevents the peanuts from losing too much oil. Next, the peanuts go through a machine called the blancher. It removes the outer skins by rubbing them between rubber belts. Then it splits the kernels and removes the heart of the peanut, which has a slightly bitter taste. But what's discarded doesn't go to waste. The skins go to farmers for pig feed, and the hearts go into bird feed. The peanuts land in a big stainless steel hopper. From there, they drop down into the grinder to be ground into a paste. At this point, the other ingredients go in: salt, sugar or another natural sweetener, and a small amount of hydrogenated vegetable oil, which acts as a stabilizer to keep the peanut oil from separating and floating to the top of the jar. Peanut butter contains no artificial coloring or artificial sweeteners. It has no preservatives either, yet doesn't need to be refrigerated. The peanut butter is finally ready. All that mixing has heated it up to 60 degrees Celsius. It goes through a cooling system to bring it down to 38 degrees. Now it can go into jars. Peanut butter is a healthy, protein-rich food with plenty of vitamins, minerals, and fiber. It has no cholesterol, but it does contain fat. The good news is that more than 80% of that fat is unsaturated. In other words, good fat that may actually help lower certain cholesterol levels in the blood. The bad news is that the rest of the fat content is trans fat or bad fat. It comes not from the peanuts themselves, but from the hydrogenated vegetable oil that's used as the stabilizer to keep the peanut oil from separating. If you want to avoid that, you can eat all-natural peanut butter, which doesn't contain a stabilizer. You'll just have to stir the peanut oil that collects at the top of the jar. Once the jars are filled with peanut butter, they go through the capping machine. The caps have an aluminum seal inside. As the caps pass through a heat machine, the seal drops down and adheres to the top of the jar, creating an airtight seal. A machine prints the production date and the expiration date. These unopened jars of peanut butter will stay fresh for 1 whole year. A household light bulb creates light through a metal filament. A high-intensity industrial light bulb uses not only a filament, but also coils, electrodes, and mercury vapor. It's more durable, but needs a cool-down period before relighting. In 1809, a British chemist invented electric light. Over the next few decades, other inventors produced electric lamps and bulbs, but the light didn't last very long. The big breakthrough came in 1879, when Thomas Edison invented a carbon filament that burned for 40 hours. Then, just a year later, he produced a bulb that burned for more than 1,200 hours. That finally made electric lighting feasible. They start by making the coil support through which they'll later thread the filament. They take a glass rod 11 millimeters long and heat it up enough to insert a pin just 28/100ths of a millimeter thick. The pin is made of tungsten, a hard metal that won't melt under high heat. The rod and pin go into a machine that heats the glass and presses it into a mushroom shape. Then they insert tungsten wires, just 0.0118 millimeters thick, 3 or 6 wires depending on the model of the light bulb. They cut the wires to the required length, which also depends on the model. Then they curl the ends into little circles. The coil support is finished. Next, they build the mount onto which several other parts will be assembled. They weld on the arc tube, a quartz tube containing a coil, electrodes, gas, and mercury. Next, they weld on the bimetal switch, which cuts the current to the coil in the arc tube. Then they weld on the coil support they prepared earlier. They bend the coil support down to receive the filament, which is made of tungsten. Now they weld one end of the filament to the mount and feed the other end through the little circles of the coil support, then weld it onto the other side of the mount. The mount is now fully assembled. Next, they apply a specific amount of pressure to the bimetal switch to calibrate it. They submerge the finished mount in alcohol to remove any dust or other contaminants. They let it dry for 10 minutes, then apply a liquid called zirconium getter. This draws moisture away from the filament. It's finally time to put the mount in the glass bulb. The sealing machine cuts off excess glass from the bottom, then melts what's left until it attaches to the mount. How will this light bulb work? The electric current travels through the filament to the coil inside the arc tube. The coil warms gases, which then vaporize the small amount of mercury. The mercury vapor then conducts the current from one electrode to another, creating light. The bulbs are made into different shapes and sizes. A machine blows air into the hot glass while a mold creates the form. A special flame lets the glass cool slowly so it won't become brittle from the stress. They print the wattage and voltage on the bulbs, then run them through an oven at 500 degrees Celsius to draw out any humidity or impurities that may be caught inside. Then they go through what's called the tipping torch. It seals in nitrogen gas, which prevents the filament from overheating. Now the bulb is ready for its first test, a 10-minute burn to make sure it operates properly and there's no air inside. Finally, it's time to attach the socket. They apply cement on the base, then hook up the bulb. The bulb passes through a flame that cures the cement. The next machine cleans the socket with acid, so it can be soldered at 2 points. The finished bulbs are put aside for 48 hours, then retested before being shipped out. A day on how it's made. Combination locks. Security that's got your number. Pottery. When they made these, they didn't throw out the mold. Recreational vehicles. Comfy accommodations that go the distance. And erasers. Mistake menders that tend to rub off on you. Combination padlocks are what students depend on to protect their lockers from thieves and pranksters. Combo locks are functional, yet fashionable. Like everything else marketed to teenagers these days, they come in a variety of trendy colors and designs. The combination lock's main locking mechanism is called the base plate. It's comprised of 7 components. That black piece, called the lock bolt, is what slides over to free the shackle when someone dials the correct combination. They rivet the base plate components into place so the lock will stand up to repeated use. Here are those components before assembly and after. They secure the assembled base plate into the casing. Then they install the trip lever spring. It's what automatically scrambles the mechanism every time the lock is closed. They fit the shackle through holes in the casing, positioning one end against the trip lever. They fasten the other side with a tiny steel bar called a yoke. The lock's combination function is made up of 3 stacked discs called tumblers. Here, the first 2 go in. Next, they grease the shackle so it'll slide in and out easily. Sometimes they customize the face of the lock. Those numbered dials used to come in just boring standard-issue steel. Today, they can have colorful designs, even a school's logo. The printing machine uses a 4-color printing process, applying 1 color at a time. The painted dials get 2 coats of clear varnish to harden and protect the paint. While that's happening, other workers assemble the dial components. First, they take the indicator button and attach it to the dial. Then they take the 3rd tumbler and rivet it to the back of the dial. This tumbler will control the movement of the 2 other tumblers inside the lock's casing. All 3 tumblers have V-shaped indentations. The correct combination aligns those V's, allowing the lock bolt to slide over and free the shackle. Each tumbler has a code number stamped on the back. The number corresponds to the location of its indentation. They program each lock's 3 tumbler codes into a computer. The computer then randomly creates a combination that will align the 3 indentations. There are more than 50,000 possible combinations. The system prints the combination on a sticker, along with a barcode. The barcode is programmed into a central computer, where it's recorded with the lock's serial number. The guts of the combination lock are finished. Now it's time for the final assembly. They put the dial onto the casing. Then a forming tool presses down on the casing's rim, folding it tightly over the dial. A computer-guided machine then engraves a serial number on each lock. Some factories do random quality control checks, but this company verifies each and every combination lock by hand. That's quite the procedure, considering this plant produces more than 10,000 locks a day. You can bet somebody's got pretty sore fingers by quitting time. As early as 11,000 BC, man was making utensils out of clay. This was the birth of pottery. Modern pottery is divided into three categories: porcelain, stoneware, and earthenware. What differentiates them is the mixture of clays and the firing process. This earthenware piece starts with a technical drawing based on an artist's conception. Following the specs, they use a series of specialized tools to sculpt a plaster model on an electric potter's wheel. They check the diameter with calipers. The model is 7% larger than the finished piece will be, to compensate for shrinkage that will occur during drying and firing. They sculpt some parts by hand and glue them on. Using this model, they cast a master mold made out of a rigid type of plaster called gypsum. They now use this master mold to cast a production mold out of rubber, or in this case, plaster. First, they pour in the plaster, using their hand to break up any air bubbles that would cause defects in the casting. They leave it to air dry in a warm room overnight. Once it's ready, they can extract it, a delicate operation that takes 15 minutes. This production mold has to cure for 48 hours before going into service. It'll be good for 200 castings. And it'll be identified by the model number on its side. Earthenware is made of talc, a mineral called methylene cyanite, a dark beige clay known as ball clay, another mineral called silica, and a white clay known as kaolin, all mixed with 40% water. They pour the mix into the production mold with careful, even pressure, again to avoid creating air bubbles. The plaster mold slowly absorbs the water, leaving behind a moist earthenware lining half a centimeter thick. After about a half hour, this lining hardens and they can dump out the surplus liquid. They cut off the excess earthenware at the top. Then, after another 45 minutes or so, extract the piece from the mold. Workers have to handle the earthenware gingerly, with even pressure. If one finger presses just a bit too hard, it'll show up as a dent, but only after the piece is fired. After a 24-hour drying period, workers then carefully shave off the seam left by the two halves of the mold. They rub the piece on wet stone to even out the top and bottom. Then they smooth the surface with a wet sponge. Unlike stoneware, which comes out glossy after firing, earthenware remains dull. So to make it shiny and colorful, they apply specialized glazes. and enamel paints. Finally, they spray the piece from top to bottom in a transparent glaze to give it an overall sheen. Then it's off to a room-sized oven called a kiln for an 8-hour firing, during which time the temperature climbs to more than 1,000 degrees Celsius. Then a 2-hour cool down. The intense heat activates the pigments in the paints and makes the colors come alive, turning what was once a lump of clay into a work of art. Traveling in a recreational vehicle is like having your own personal motel on wheels. RVs are either motorized or towable. Towable ones range from folding tent trailers, known as pop-ups, to more elaborate travel trailers, complete with fully equipped bathrooms and kitchens. To make a travel trailer, workers first cut steel bars to build a frame. The saw has to be drenched in coolant, or it'll overheat due to the intense friction. They drill holes for the bolts and screws they'll later use to attach certain components. Then they solder the frame parts together. They run electrical wires through the frame, lining the holes with rubber grommets to keep the wires from rubbing on the sharp metal edge. Next, they install metal brackets to hold the water and septic tanks in place underneath the trailer. Then they torque the wheels to the axle. Now they install the gas lines. The stove, the fridge, and the heating system all run on propane. Next come the water and septic tanks, made of polyethylene, a heavy-duty plastic. They cut a hole in each tank and screw on a fitting. The tanks sit directly on the frame. The white ones for drinking water, the first black ones for the shower and sinks, and the second black ones for the toilet. To build the floor, they put down a waterproof membrane, then a spruce frame insulated with fiberglass wool, then 5/8 plywood, cutting vent holes for the forced air heating system. After sanding the joints and gluing down linoleum, they install the cabinetry and furniture. The plumbing fixtures come next. They connect to water lines coming up from the tanks beneath the floor. The water system is driven by an electric pump. While some workers put up the pre-assembled walls, others run wiring for the lights and appliances. The inside wall surface is vinyl paneling. Drywall would be far too heavy for an RV. The paneling's mounted on a pine structure insulated with fiberglass wool. They cover the outside in aluminum siding. Then they complete the electrical wiring for the lights and appliances. Now it's time to install the roof. Another pine structure with fiberglass wool insulation, covered with a thin wood called luan that's reinforced to withstand the extra weight of roof cargo. They cut out the various ventilation holes. Then apply a layer of glue. Then lay down a high-performance waterproof rubber membrane, nailing it down along the perimeter. They install vents for the toilet, the refrigerator, and for air circulation. They caulk all the joints and around all the vents. Last but not least, the windows, doors, awnings, and any optional equipment. Workers check the water, gas, and electrical systems, then do what's called a seal test. A special machine applies air pressure from the inside out. Wherever water bubbles, there's a leak to be repaired. With all the upholstery and other decorative elements in place, this comfortable travel trailer is ready to hit the road. Make no mistake about it, an eraser is a student's best friend. Whether it's attached to the top of a pencil or on its own, only an eraser can quickly rub out an error. White erasers are made of flexible vinyl, while pink erasers are made of synthetic rubber. In 1736, a French explorer observed South American native Indians using a certain tree resin to make bouncing balls. He brought this resin back home, and before long, Europeans discovered it could rub out lead pencil marks, hence the term rubber. There was just one problem. After a while, rubber would rot. That dilemma was solved a century later by one Charles Goodyear, who developed a curing process to prevent rubber from rotting. A lot of ingredients go into making a simple pink eraser. Carefully measured fillers, accelerators, curing agents, oils, coloring, and the main ingredient, synthetic rubber. They start by putting a batch of rubber into a mill. The rubber passes repeatedly between large heated rollers. They throw in any defective erasers from the last production run, recycling them into this new batch. Then they add sulfur as a curing agent, accelerators to help the sulfur do its job, and red coloring. They blend everything for 5 to 10 minutes until the mixture is the consistency of heavy dough. Next, vulcanized vegetable oil. That's vegetable oil treated with sulfur, then regular vegetable oil, then calcium carbonate as a filler. When the color and thickness are just right, workers remove the rubber, which by now is hot and soft as a result of all that milling. They leave it to cool and harden at room temperature for about half a day. When the rubber's ready, they cut out large squares, each weighing between 5 and 8 kilograms, depending on the thickness of eraser the client has ordered. The squares go into a steam-heated press to cure for about 20 minutes at 163 degrees Celsius. The pressure compacts the rubber, while the intense heat hardens it. They trim off the excess, then submerge the hot rubber squares in cold water to stop the curing process. To make erasers that erase both lead and ink, they cut beveled strips from 2 batches of rubber, one pink and one blue. The blue contains pumice, which gives it that extra abrasiveness to erase ink. They pair up each pink with a blue to form a 2-color strip. Then it's into the steam press. After 12 minutes, workers remove the trays, trim off the excess, and submerge the strips in cold water to stop the curing process. Then an automated machine chops the strips into pieces the size of erasers. Now back to the all-pink erasers. The rubber squares come out of their cold water bath and go through a machine that cuts strips with beveled edges. Then chops the strips into erasers. From there, the erasers drop into a giant barrel. Workers throw in some talc to prevent them from sticking together. Then they set the barrel spinning for 3 to 5 hours. As the erasers tumble against each other, the abrasion rounds off their edges. The last step is printing. A machine stamps each eraser with the company name and the model number. It's not the rubber that gives the eraser the ability to erase, but rather the vulcanized vegetable oil that's in it. That's what makes the eraser crumble when rubbed on paper, taking away the pencil marks with it.
Hello everybody, I'm Mark Tewksbury, your host for this program. Our goal is to reveal the methods and materials that turn out the everyday products we see around us. If you think you know something about these items, you might be in for some surprises. There's a whole world of things waiting for us to discover here on How It's Made. On today's show, hearing aids, 3D puzzles, rubber mats, and toilets. You often hear people say that we should cut back on eating so much sugar, but then what would we do with it all? Believe it or not, we could add it to our irrigation systems to fight pollution. Sugar nourishes soil bacteria without forming greenhouse gas. Who knew? It's easy to take sound for granted until you lose it due to a serious hearing disorder. Thankfully, this tiny hearing aid brings back the music. Loss of hearing causes a serious handicap, but happily it can be remedied thanks to hearing aids. But before fabricating the aid, the degree of hearing loss must be precisely measured with this apparatus called an audiometer. So they make a mold of the ear canal. To protect the eardrum, an autoblock is inserted. Next step is to pour in a silicone impression-making material. It solidifies and is then removed from the ear. This congealed mass, representing the ear canal, is then soaked in warm wax to obtain a positive imprint. Then the silicone container is filled. The silicone hardens in only 10 minutes. The hardened silicone block is removed, and the excess of the imprint is removed so that only the essential part is retained. The imprint must slip easily into the ear. It's now the molding stage for the hearing aid. Acrylic is poured into the mold before placing it into this ultraviolet oven. Without emitting any heat, this oven hardens the acrylic. Here is the raw prosthesis without its electronic components. This plan details the electric circuit of the amplifier. Holes are pierced for the volume control. These components are tiny. Here's the volume control, the miniature microphone that captures sounds, and the earphone which functions as a speaker. This tiny braided wire of 7 conductors is soldered to the amplifier and the other parts of the prosthesis with pewter. The hybrid circuit is inserted into a silicone casing, which assures it protection. Then the wires are soldered to the speaker, and they verify the proper functioning of the volume control. A hearing aid must be very discreet. That's why they cut the excess with a diamond disc. They also remove the roughness with fine sandpaper. The holes we see here are used to vent air from the earphone. This silicone tube is used to make the vent. Acrylic is poured onto the tube to form a tunnel. Ultraviolet light is used to harden the acrylic. Afterwards, the tube is removed. This hole is used to position the fastener, a small wire which allows for removing the hearing aid from the ear. Then the battery is installed. Only a few parts, such as the microphone, remain to be put in place. Then everything is delicately assembled into the interior of the prosthesis. The two parts of the hearing aid are then glued together. Ultraviolet hardens the glue. The plate used to position the prosthesis components is cut away with a drill. Then the hearing aid is manually polished to make it perfectly smooth and comfortable. The prosthesis is now completed. There remains one important step, verifying its electroacoustic characteristic. It's with this analyzer that they validate that the hearing aid conforms to the original prescription. These minute prostheses allow us to solve the main hearing problems. Microfabrication of a single unit requires a little more than 2 days of work. Remember putting together these simple 60-piece kids puzzles? Well, now imagine doing a 1,500-piece puzzle, 3D, with the pieces going up, down, and even sideways. Now there's a challenge. Flat puzzles are well known by everyone, but 3D puzzles present a different challenge. These three-dimensional puzzles are first conceived with computer software. Good blades are needed to cut puzzle pieces. Here are the blades for the master die, which will cut out printed sheets of different models. This rubber will be used to eject the die. The master cutting die is unique to each puzzle. It is the specific pattern used to make the puzzle. They measure it meticulously to obtain a perfect register. It's imperative that the die not move during the cutting. Otherwise, the pieces would be cut at the wrong points, so they very firmly secure it in place. The carbon of the die is positioned. It's somewhat like printing the master. Alignment is again verified, a highly important step which assures the quality of the final product. Finally, they install this large metallic plate, which is the cutting base. It will be on this surface that the master die will strike. Once measurements are finished, the drawer of the die is slid into place. This press cuts the pattern seen on the puzzle. Here's how it works. The sheets, or printed cardboards, go into the drawer one by one, where they are cut according to the master model. We clearly see the press making the cut in the puzzle sheet. The cut sheets pile up on one another, and at this checkpoint, they verify the precision of the cut. They make sure that every piece is correctly shaped. Now they go to the foam support of the puzzle. This guillotine is used to cut the polyethylene sheets onto which they will glue the cut images. Foam sheets are inserted into this laminator, heated to 232 degrees centigrade. The sheet with the design on it is glued onto the foam with a thermosetting adhesive. Now they glue the printed sheet onto the foam sheet. Once the adhesion is finished, the puzzles are stacked on one another and they proceed to the unbuckling operation. By pulling, they remove the surplus cuttings. The same design is printed several times on a sheet, so they must separate each puzzle. This step is called the reduction of the models. Now the pieces have to be separated. This decorticator handles this task and sends the pieces down a chute. Packing cartons arrive already made up, and the puzzle pieces are placed in their boxes. No less than 15,000 puzzles are produced here each day. Since it began operations, the company has created more than 300 different puzzle models, from quite simple ones to much more complex designs. The largest of them contain a total of 3,146 pieces. And you need real patience for this one. Ever wonder what happens to old used tires? Believe it or not, we now use them to manufacture rubber mats that can cover an entire arena. Now that's great recycling. Used tires are a real source of pollution. This pile represents about 100,000 of them. At any rate, these tires will have a second life. They'll be recycled to make rubber mats. Each day in this factory, they recycle 15,000 tires into mats. Tires have to be reduced to little granules, but first, this conveyor feeds the tires into the washer. Tires are washed with a water-based biodegradable preparation. Then they're sent to the shredder. The shredder has 2 rows of large teeth. These grind up the tires into pieces. This shredder is able to cut up almost 1,000 tires an hour. They come out as fairly good-sized pieces of tires, which are then shredded a second time. Metal is magnetically separated from the rubber, and the metal pieces are recycled at another factory. Other components of the tires, such as fiberglass and nylon, also have to be separated. They use a sifter to get out unwanted rubbish. Recuperated rubber particles purged of foreign materials measure about 2.5 millimeters. Some 16 tons of tire particles are piled up in this recycling depot. But the particles are still too large to be used. They're sent to a secondary shredder's supply tank, where they'll be reduced even further. This tractor feeds the secondary shredder. Grinding action produces a kind of rubber powder. The powder is spread out on these enormous molds. This mold has a length of 7 meters and a width of 1.2 meters. Thickness varies according to the product being made. The molds filled with rubber powder are stored in this loading magazine of the press. Once full, the molds are sent to the rubber mat press. Here's the mat press. The powder has to be cooked at a very high temperature for about 30 minutes. Cooking time depends on the product being made. The cooked mat goes through the unmolding unit before being sent off to cool. The rubber mats are still extremely hot. They're cooled with jets of water for a period of several minutes. The cooled mats can now be sent to the next department. This conveyor in the cutting center positions the mat before it's cut. The mat is vibrated to eliminate any surplus water. Each rubber mat is now cut up into 3 pieces. The cut mats are then stacked into a pile and stored before being shipped. The company also makes mud guards. These are fabricated the same way as the preceding mats. After having been cooled in water, but while they're still warm, they remove the surplus rubber. This operation is called notching. Hard rubber rings are also produced at this facility with the same fabrication methods and, as always, from old used tires. Over a 12-hour period, this facility makes no less than 12,000 rubber mats from old recycled tires. This translates into good news for our environment. This household item is something you might take for granted. But can you imagine life without it? The toilet, a shiny, sculpted marvel of manufacturing. The first public restrooms appeared in ancient Rome when the Emperor Vespasian built latrines. Such public urinals became widely known as Vespasiennes by 1840. In 1775, the invention of a water flush system created toilets somewhat resembling today's convenience. The valve and siphon were added in 1784 and the septic tank in 1896. A toilet is an everyday object whose fabrication requires several days of work. It involves assembling several molds, called tools. Each new product requires the design of a master plaster mold, from which they will produce a plastic tool. This latter will be used to create plaster duplicates used as production molds. The plaster production mold of a toilet is made from 6 different tools, which have to be assembled. Their lifespan is only 2 months. The process begins with a mixture of water and plaster according to a precise recipe. Then the liquid is poured into this filling hole of the tool. Once the plaster hardens, they can proceed with unmolding. They strike the end at the junction of the plaster mold and the tool with a rubber hammer so as not to damage the plaster. The pieces are gently assembled. The toilet softly takes its shape. It's in this same mold that they will later color the clay. Then they install tensioning straps. Little blocks are inserted between the mold and the strap to increase the tension. The mold will soon be filled with liquid, and they thus prevent any distortion. Here a new recipe is being prepared. This time it's a slurry, a composite of clay and silica. This preparation is spread out over 48 hours. Now they install the core, the upper part of the mold. They can now proceed with the filling. This copper distribution pipe, connected to the tank containing the slurry, permits the filling of several molds at a time. They need about 20 kilos of the mix per bowl mold. After an hour, The slurry has attained a thickness of 1 centimeter. The plug is pulled to allow the excess slurry to run out. They can now unmold the still fragile piece. This thicker slurry is used to adhere the two pieces together. They cut the holes and unmold the ensemble. The toilet is now molded. Then, to obtain a perfect appearance, they remove the little fillet formed by the surplus adhesive slurry. The toilets air dry for 36 hours, then in a warm air dryer for 12 hours. Finishing must be impeccable. They carefully sand the surface to make it perfectly smooth. A vacuum draws up the dust. Then with a jet of compressed air, dust and debris are blown away. Bowls are hand-painted in a special room. As for the water tanks, they're painted by an automated robot. This truck carries the different parts to the final fabrication stage, baking. The toilets remain in this oven at the very high temperature of 1,176 degrees centigrade for 23 hours. It takes this long to fuse the clay and silica. The paint then becomes hard and shiny, and it's all done. The toilets in the different bowls now take on shapes more elegant than in the past, but the fabrication of each one of them will have the same basic construction steps, involving 20 kilos of slurry and almost 4 days of labor. If a picture's worth 1,000 words, I hope what you saw today speaks for itself. Our goal was to take you behind the scenes to the world of manufacturing. I'm Mark Tewksbury.